Okay, for the first talk of this session, we have Sebastiano talking about unraveling a massive node of the cosmic web with the help of Quasar Fluorescent Emission. So, take away, Sebastiano.
Okay, so thank you very much. So before starting with the talk, I would like to thank Avishai, Joel, Sandy, and Colin, the organizer of this meeting, for organizing it and giving me the opportunity to come back to Santa Cruz. Many of you know it's my second home. Last time I was here was 2019, so many things happened after that in the world, but also in my life. Coca, where I started a new research group, thanks to a ERC consolidated grant, the one in 2019. I've now, is there a team of great people. You have the names here. There will be pictures later on during the talk, and there is also Stephanie giving a talk later today. Okay, but what I'm going to show you today is how we can use quasars to make the dark universe, the cosmic web, and everything we dreamed of seeing before visible with our optical telescopes. For the one of you that know me, I've given in the past talks where I show you individual filaments. I will present you today very recent result where we can finally see multiple filaments on cosmic scales of Kumui megaparsec converging into a massive node. Most of these results will not be online, so there will be no PDF, there will be no video of this. So pay attention to it, otherwise you will miss it, or you can always ask me. Thank you for being here this morning very early. I hope that you'll be rewarded with something nice. Okay, so let's get started. This is my talk outline. After a brief introduction, I will show you, tell you a bit the history, what I've been doing so far using Muse. And then in the second part of the talk, I'll show you how we'll be able to enlarge the view and detect megaparsec scale filaments in emission. And I'll show you very recent results with JWST and multimodal wavelength observations that are now giving us the opportunity to connect for the first time the galaxy and the cosmic web, cosmic streams and galactic flows. Finish with a summary and a brief. But let me start with this picture. This is a conference about galaxy. It's a galaxy workshop, so I had to start with galaxies. This is a beautiful picture that has been obtained recently with JWST. We have many of these. As we all know, however, as beautiful as it is, this is a very limited view of our universe. We all know that there is much more than this, and if we'll be able to see it, it will look like that. A picture like this, which is not a real picture, is coming from simulations, but if you are patient, by the end of the talk, you will see a real picture that look similar to this, okay, taken with a telescope. We know that the universe is an interconnected web that connects all galaxies, and this is driving galaxy formation and evolution. If we are able to take a picture of this, we can address questions like, how do galaxies get their gas? What are the density, morphology, and temperature of the CGM? How are galaxies connected to each other? What are the morphology and small-scale properties of the cosmic web? In order to address this fundamental question for galaxy formation evolution, we need direct imaging. We need to take a picture of this. So how do we do it? We've been doing it since many decades now, but let me start with an example taken from our own galaxy. As in the ISM, you have some regions that are illuminated, and you can see it thanks to some little star here. In the universe, you can imagine that there could be regions where you can have these gigantic H2 regions where the IGM is also illuminated. Of course, little stars will not be enough. What we will need are hyperluminous quasars. And as I'm going to show you today, by looking around hyperluminous quasars, we can illuminate the IGM over megaparsec scales. This is sometimes referred as fluorescent lava-knife emission. And the important thing about this is that it will give you the morphology and all the structure of the IGM, but especially it will give you a way in which you can gain information about the density of the intragalactic gas, because the surface matters that you will detect is proportional to the density square, and also depends on the clumpiness of the medium under the resolution scale. So a constant topic of my talk will be measurements of density and clumpiness, and this thing will come back, and maybe the analogy with the interstellar medium is not just a fantasy, there is something more, as we will see later. So, so the trick is then look around bright quasars. And that's what I've been doing since many decades. And actually, my story passed through here in Santa Cruz. Andrea is laughing because no, decades, yes, decades now. And I cannot refrain from showing this. This is our first experiment done with LRIS narrowband imaging. By looking around quasar, we've been able to detect, indeed, in few cases, but this is my first observation at Keck, gigantic Lyman alpha filaments with sizes of several comuni megaparsec around quasars, in this case 2 quasars, and here multiple quasars. This is the Slug Nebula that everyone knows here in Santa Cruz, but also all around the world. It's a good publicity for our mascot. And this is the Jackpot Nebula that was also discovered with ARIS. The important thing here is that the morphology looks like filamentary on large scales, but the surface radius is very high, which implies high densities, which is something that will come back, in particular as high as the interstellar medium. The field has been revolutionized in the last few years by MUSE and the Keck Cosmic Web Imager. Nowadays, this has been a very huge effort, build a narrowband filter, all the rest. Now you can point any quasar in the universe, and you get giant Lyman alpha emission. This is a collection of the first 20 nebula we've been able to find around quasars. Quasars is here, where this black spot is, has been removed. And now we have more than 200 giant quasar Lyman alpha nebula. Every quasar we look at shows circumgalactic medium and IGM in emission. So 20 years ago we thought it was difficult. Now I can tell you it is easy. You just have to look around quasars. And how does the CGM looks like? Balls or fried eggs, I don't know, shape. We don't see streams, very shy, on small scales, but on large scales we start seeing filaments. So in the inner regions, spherical, in the outer regions, some filamentary structure. This is only 1 hour of MUSE observation. This is, of course, much more than just an image. It's an integral field spectrograph. So rather than just an image, I can show you a 3-dimensional view of these filaments. This is the Nebula 3 that shows an interesting filament here. This is what happened when we extracted in 3D. This is the spatial view. And this is now the velocity view. We can see that the filament is coherent in velocity space. This is just 1 hour of MUSE. Later today, I will show you a 15-hour version of this nebula, which shows many interesting features. But this is just to give you a glimpse that we have 3-dimensional information on the IGM and CGM. They're not just pictures. So the question is, the surface mass is very high, so how dense or broad is the gas density distribution in the CGM? To address this question, we need more lines, not just Lyman alpha. So in the last year, we have been looking at H alpha from hydrogen and helium. And this is an example from the Slug Nebula. We have been able to detect H alpha. It's been difficult from the ground using MOSFI. This is a ratio 2.4. And we've been able to detect helium-2. This is an IFU optimally extracted image. The line ratio is consistent with recombination radiation, Lyman alpha over H alpha, but the big mystery is that the helium-2 versus H alpha ratio is very low, less than 8%. And this low ratio, there is no way in which you can explain it using photonization models with single density, which is telling you maybe something obvious, but it was not obvious 10 years ago. The CGM is multi-phase. You need to have broad density distribution. And how broad? Well, our models, simple models, can reproduce this ratio if you have a log normal distribution with a sigma that is larger than 2.5. So the answer is extremely broad, extremely turbulent. You will need the CGM that is as turbulent as the interstellar medium. Sounds crazy, but this is what the universe is telling us. So how can we achieve and maintain such large turbulence in the IGM? We have been discussing turbulence yesterday. I don't have time today to go into that. I'd be very happy to discuss with you. Filamentary accretion, near Mandelker, Avishai worked on this. We also worked on it. And Stefan is going to touch on this point later on again. But you might tell me, oh, this is just one object. Maybe this object is weird. That's why we looked into more nebula in the past. And together with Andrea Travascio, working in our group, we've been able now to find, looking deeper around quasars, a large statistical sample of helium-2 nebula. This is helium-2 Lyman alpha, helium-2 Lyman alpha. And the line ratio for all these nebula is consistent with the slug nebula ratio. They are all very low. This is the first statistical sample that is confirming that the CGM needs to be turbulent or to have a very broad density distribution. In addition, because it's a no-resonant line, we also get velocity dispersion information. And the helium-2 velocity dispersion is similar to the Lyman alpha one. Similar, I mean, there is a normalization effect, which is telling you that Lyman alpha can be used for kinematics if you do it in the proper way. And Stefan is going to tell you how to do it later. Yeah. Yes. Sorry. Yeah, it's very, very later here. Yeah. I've seen it, but too quickly. But sorry about that. It's a good point. Left is helium, and right is Lyman alpha. Yeah. Very good. So this is about the CGM, but I promise you something about the cosmic web. So the snapshot survey that I showed you at the beginning was only to select the best one or two candidates to go deeper than with MUSE, larger, and to detect filaments on megaparsec scales. So what I'm going to show you now are the results of our efforts in the last years. And these things you're not going to find online or in the video, so maybe now it's the moment to pay attention. This was our previous observation, only 1 hour of MUSE. Now we went deeper on the nebula 3, and we enlarged our view. So what I'm going to show you now is the same thing, but in a 1x3 mosaic and 15-hour MUSE deep observation. Are you ready? So we saw some hints of filaments here, maybe one filament. When we go deeper and larger, that's what we see. Now we see 3 filaments. So this is the moment in which Avishai should pay attention. We see 3 filaments, and the nicest thing of all is that the nebula got much larger and is now 2 million megaparsec inside and connecting the quasar, which is here, to a galaxy which is far away. When I see filaments, you say, what are these filaments? It looks like there is something with a hole in it. Well, when you look in 3 dimensions, you see that actually these things here are overlapping filaments, which are clearly separated in velocity space, that are crossing and are joining somewhere here close to the quasar. So there is an interesting kinematical structure here, which I can only give a glimpse of it in this movie, but if you are more interested to look into that, we can have a look at it. The interesting thing, of course, about these nebula is that these filaments are kinematically narrow, and we have now all the kinematical information about this. But these are like 3 filaments coming into the nebula. So when we saw this nebula, I said, we made it. It's fantastic. Simon Lilly, which said, well, but we need another one. I mean, one is not enough. So why don't we go deeper around another nebula? I said, why not? I mean, we have the GTO time. So we selected another nebula, the nebula number 1, which showed some interesting, possibly something here, but otherwise they look particularly nice. So we looked with our MUSE GTO, and we went now much larger, 4x4. We went deeper. We spent 40 hours of MUSE, and we detected this. So the central thing was here, but in addition with the central thing, now we see filaments extending all over the Muse field of view. Please don't take pictures. 4 megaparsec extending far beyond the Muse field of view. We also see narrow filaments going in this direction, and this thing is definitely much more complex than what we saw before. No narrow filaments, but very broad filaments with sizes of megaparsec. Clearly, this structure looks a little bit different than the one that I showed you before. The very interesting thing about this is that when we look at galaxies in the field with Muse, we have the full spectroscopic coverage. We actually discovered a lot of galaxies. The galaxies, Lambre galaxies, are this yellow square here. They trace the filaments, or the filaments trace the galaxies, I don't know. Among these, 3 show type 2 AGN signature in their spectra. So this is a triple AGN. So it looks like this is a very rich field. And this is the reason why in the last 2 years, I spent almost all my time building one of the largest multi-wavelength deep survey around the quasar. This quasar is at minus 42, so it's in the middle of nowhere. It's a region of the universe that was never basically observed before. What we got in the last 2 years, because we think this is exceptional, and I'm going to show you exceptional results in a few minutes, we got 650 kiloseconds of Chandra X-ray to trace all the possible AGN in this field, 45 hours of ALMA to study CO423 and dust continuum, to trace dust obscure galaxy population and all the possible population in this field, 24 hours of GWST near spec to detect H-alpha emission in the filaments and in the galaxies for the first time. And we got the observation 3 weeks ago. So I'm going to show you really, really fresh results. Yeah, Sandy. You mean this thing? Oh, sorry. Underlined is a white light image of the field with Muse. So these are stars and galaxies. It's basically a white light image. So it's like a broadband image. The contours are the Lyman alpha things. And the yellow squares are the ones that have been selected to be at the redshift of the quasar. Yeah, I missed a few very important information. Yeah, so these yellow things are galaxies at the redshift of the quasar. These things are foreground, background stars. Yeah, I think this is a star. Yeah. Okay, so is this addressing your question? So near spec, I'm going to show you the results, and then all the possible multi-wavelength data. Deep HST, 22 orbits, Magellan Megacam, Force OCI, all possible bands, and GWST NearCam that I'm going to show you later. So I'm going to show you now quickly these results in my last 5 minutes. Let me start with the multi-wavelength information. We want to know where is this nebula, where is this structure sitting? For this, we need to enlarge our view. We did, Marta Galbiati, PhD student in our group, did a very nice Lyman galaxy survey using Force and Hawkeye. This is the position of the nebula, and with the filaments, this is the previous Muse observation, and these are now the new field of view, and the colored Voronoi tessellation things tell you about the density of galaxies. So you can clearly see that there is an overdensity of a galaxy extending in the same direction of filaments. So the filaments here are just the node, the central part of a much larger structure that we are detecting now with galaxies. And this thing actually reminds of a massive structure we see in Eagle. This is a mock observation, mock Lyman alpha map made by Stephanie. See here, but she's also sitting there. And this is the most massive halo in Eagle, and it looks like the structure is indeed similar. This has been made for a proposal, so things have been laid out in a particular way, but this may be a very massive system, 10 to the 13 solar mass halo. Let's see if I take another picture, that's fine. And there is a huge overdensity of Lyman galaxies here. This is the Lyman galaxy in this field compared to the average population. So this is a very overdense, this is a very rich field, one of the largest overdensity we have found so far in galaxies at this redshift. This is redshift 3, by the way. Then I can show you also some ALMA results. So this is work done by Antonio Pinsabene. Here you see flipping two images. This is the Lyman alpha filament, and underneath there is the JWST NIRCam image. All these squares and circles are ALMA detected sources at the redshift of the quasar. We have several CO423 line emitting galaxies and dust selected galaxies. Most of them are in the filaments, some of which are in a very rich region here that I'm going to show you later, which is a very surprising and interesting region. But what was very surprising was what we found was hidden under the quasar PSF. The quasar is very bright, and when we looked with ALMA, we didn't see a single source, the quasar, but we saw this. The quasar and a companion 1 arc second away, and the companion is a massive rotating disk. This is the velocity map, looks like a perfect velocity rotation curve. It's very dusty. It is elongated in the same direction of the filaments, and to me it's very surprising why a massive rotating disk is sitting few kiloparsec away from one of the brightest quasars in the universe. What this thing is doing that. I was not expecting to find it there. So something to think about. Is at exactly the same redshift of the quasar. So it's not a superposition. The overdensity is also very large, factor of 30. So this is one of the largest overdensity of CO emitters found at this redshift. In the X-ray, the story is the same. We detected a lot of X-ray sources, multiple AGN. We have 5 X-ray sources in 1 Archimedes square, and this is the 250 times more overdense than the field, and is even more overdense than the spider web, SSA22, and anything we've been finding so far. There are very interesting results also in the X-ray. If you want, we can discuss it later. I want to spend a few minutes now on the NIRCam result, which have been obtained by Weishen Wang, who you might know, was also visiting Santa Cruz, is now in Milan Bicocca. I'm going to show you some HST and NIRCam imaging we obtained. These are NIRCam pre-imaging, so just 20 minutes of NIRCam. With this, we can finally study the morphology, orientation, and properties of galaxies with respect to the filaments. So we detected the companion of the quasar, and it looks like the dust is forming disk indeed. We see the AGN in very interesting environments, possibly merger. This is another AGN, so we have the orientation and all the things you might want to ask about your galaxy formation model and evolution. This region here looked very interesting. We had multiple Lyman break galaxies in a Lyman alpha blob, and that's how the HST image looks like. Multiple clumps, but then really we couldn't believe what we saw in the JWST image instead. This is about 4 arc second wide. This is the HST F8014, and this is what we saw in JWST F1.5 micron. We saw a grand design spiral with a size of 36 physical kiloparsec. You are the expert on galaxies. 3.2, which I found amazing, that a spiral is there, what that thing is doing there. So it's a very rich field with a lot of surprises. We, of course, also have spectroscopic information because we have the near spec. We see H alpha and hydrogen 2, velocity gradients, and complex kinematics, where we see rotation. So this looks like a Milky Way, but it is a redshift 3. What is doing there in the middle of Lyman alpha filaments and all the rest? I have no idea. This is the result from 2 days ago. We also see filaments, so this is the companion, and we detect the H-alpha from filaments, and you see the kinematic structure joining to the disk. So there is a very rich field here where many of the questions of this conference can be addressed now with the data. What's happening next? Well, we have all the rest of the slits to reduce. We finally can correlate galaxy properties, all that you want, with gaseous filament properties, density, clumpiness, morphology, kinematics. We have 80 hours of muse allocated in October to trace the full structure here. And one of my dreams is to use these images also to constrain the dark matter properties. And we are working on this with Tito and Lezera. These two simulations, what dark matter, cold dark matter, and use the morphology of filaments to constrain it. So this brings us to the summary. I showed you that we can finally detect and map IgM in emission on small and large scales thanks to quasars, muse KSWI. Our observations suggest very turbulent CGM, and we don't know what are the physical processes responsible for this and what are the implications for galaxy formation. Show you this massive node with full of surprises, and the next steps include correlating all the properties we have been finding, resolving the small-scale physics, and possibly even constraining the dark matter properties with this. So there's a lot more happening in the next future. Stay tuned. Thank you very much.
All right, time for questions.
Thanks for the beautiful results. I was wondering, those galaxies you found in the filaments, are they also Lyman alpha emitters at the same time?
This is a good question. These are, we select them as absorption line galaxies because you have a huge Lyman alpha nebula. They will look like Lyman alpha emitters, but we don't know if the Lyman alpha is coming from the galaxy or from the filaments. That's the reason why we select them on the continuum using absorption lines, so we are secure about the ratio.
Okay. What kind of absorption lines?
ISM absorption lines, the usual ones. This is very deep muse observation, so we have beautiful spectra. There are many more galaxies than this. This is just the continuum selected.
Oh, okay.
Okay, we have time for another question.
Thank you. You began by saying that the quasar was the source of the ionization of the H-alpha. Is that true for the rest of the filaments, or can you tell from the illumination brightness?
This is a very good point. So the question is, why do we see this huge structure there and not anywhere else in the universe? One possible answer is that because you have a lot of illumination by multiple sources. It's like, it's like you only have one lantern on the street, or you are in the middle of a city. Who is illuminating you? I mean, there's a lot of light. So it's a kind of background thing. And that's why we did the Chandra observation. And then we did, this is exactly, probably the answer to the question. There are a lot of AGN. Yeah. Thank you.
All right. If you have more questions, as Sebastiano said in the beginning, please put it on the Google Doc that's linked in the schedule, so that we have time to, like, at the end of the session, we have time to discuss. But let's thank Sebastiano again.